Welcome to C004. Today we dive into ionic equilibrium, the chemistry of ions in solution, acids, bases, and the pH scale. This topic underpins medicine, biology, environmental chemistry, and industrial processes. Every buffer in your blood, every antacid tablet you swallow, every indicator color change in a titration, all of it traces back to the principles we are covering today. NEET consistently awards 4 to 5 marks to this area, so understanding it thoroughly pays off enormously. The pH of your blood sits between 7.35 and 7.45. That is a range of just 0.1 pH units. Drop below 7.0 and you go into life-threatening acidosis. Rise above 7.8 and alkalosis sets in. Your body has an extraordinarily sophisticated buffer system based entirely on the ionic equilibrium of carbonic acid and bicarbonate ions that maintains blood pH within this tiny window every second of your life. When you run and your muscles produce lactic acid, this buffer system neutralizes it. When you are at high altitude and breathe faster, removing carbon dioxide, the buffer compensates. Ionic equilibrium chemistry is literally keeping you alive right now as you study this lesson. There are 3 key definitions of acids and bases, and you need all 3 for NET. Arrhenius, an acid produces hydrogen ions in water, a base produces hydroxide ions. Brønsted-Lowry, an acid donates protons, a base accepts protons. This broader view allows us to discuss acid-base behavior in non-aqueous systems. Lewis, an acid accepts electron pairs, a base donates them. This is the broadest definition and explains reactions like boron trifluoride accepting a lone pair from ammonia. The pH scale runs from 0 to 14 at 25 degrees Celsius. pH less than 7 is acidic, pH 7 is neutral, pH greater than 7 is basic. The ionic product of water, Kw, equals 10 to the power of negative 14 at 25 degrees. This links pH and Po, they always add up to 14. Core concept 2, strong versus weak acids and Ca. Strong acids dissociate completely, every molecule gives up its proton. For a 0.1 molar hydrochloric acid solution, the hydrogen ion concentration is exactly 0.1 molar, and pH is 1. Weak acids only partially dissociate. Acetic acid, the acid in vinegar, is a classic example. For weak acids, we use the acid dissociation constant Ca to calculate the equilibrium concentration of hydrogen ions. The formula pH equals half of pKa minus logC comes from the equilibrium calculation with the approximation that alpha, the degree of dissociation, is small. This approximation is valid when Ca is much smaller than the initial concentration. Conjugate pairs are crucial for buffer chemistry, the stronger the acid, the weaker its conjugate base, and vice versa. A buffer solution resists changes in pH when small amounts of acid or base are added. It consists of a weak acid and its conjugate base in significant quantities. The Henderson-Hasselbalch equation is your calculation tool, pH equals pKa plus the log of the ratio of conjugate base to acid. When the ratio is 1 equal concentrations of acid and salt, pH equals pKa exactly. This is the point of maximum buffering capacity. In our worked example, an equimolar acetate buffer has pH 4.74. When we add a small amount of hydrochloric acid, the acetate ion absorbs the added protons, the ratio shifts slightly, and pH changes by only 0.09 units instead of the large drop that would occur without a buffer. Blood uses bicarbonate as its buffer. HeCO and HCOI maintain pH between 7.35 and 7.45. The ionic product of water Kw equals 10 to the negative 14 at 25 degrees, memorize this. It connects pH and Po. For strong acids, pH is simply negative log of the concentration. For weak acids, pH equals half of pKa minus logC from the equilibrium approximation. The Henderson-Hasselbalch equation is essential for buffer calculations. Salt hydrolysis is a frequently tested concept. When a salt dissolves, does the solution become acidic, basic, or neutral? A salt formed from a strong acid and weak base hydrolyzes to give an acidic solution. Strong base weak acid gives basic. Strong acid strong base gives neutral. Weak acid weak base depends on Ca and Kb values. Know these 4 cases. Your NEET strategy for ionic equilibrium. pH calculations are among the most common numerical questions in NEET chemistry. Know 3 formulas. Cold, pH equals negative log of concentration for strong acids, pH equals half of pKa minus logC for weak acids, pH equals pKa plus log of salt to acid ratio for buffers. Never confuse them. A powerful shortcut: if a buffer has equal concentrations of weak acid and its conjugate base, pH equals pKa instantly, no calculation needed. For salt hydrolysis, remember the 4 cases: strong weak gives acidic, weak strong gives basic, strong strong gives neutral, weak weak depends on individual constants. The temperature trap on Kw is a genuine NEET question type. At temperatures above 25 degrees, Kw is larger than 10 to the negative 14. 5 key points from C004. 1. Know all 3 acid-base definitions: Arrhenius, Brønsted-Lowry, and Lewis, each tested in different contexts. 2. pH plus Po equals 14, and Kw equals 10 to the negative 14 at 25 degrees. 3. Strong acids fully dissociate, weak acids require Ka calculations. For the buffers contain a weak acid and its conjugate base, maximum buffering capacity when their concentrations are equal. 5. Salt hydrolysis produces acidic solutions when formed from strong acid plus weak base, and basic solutions when from weak acid plus strong base. Next up, C005 takes us into electrochemistry and redox reactions, where chemistry and electricity meet. See you there.